If you're, we had, as you may recall, we had a lecture on Friday. That was to make up for the fact that we didn't have a lecture on Wednesday. I remember some of you here, many of you weren't. Since that was not the usual class time, I couldn't require anyone to come. And due to COVID, I can't require anyone to come anytime. However, it is a good idea to come to class because, first of all, it's live, so you have real interactions. And then you have the opportunity to interrupt me at any point and ask me questions, which I strongly encourage you to do. I've been strongly encouraging that all semester. If there's anything that you don't understand, the best time to make that clear is while I'm lecturing and say, no, stop, I don't understand that. For those who have missed class, I would hope that you've watched the videos since then. We take the videos for a reason, not just because we have extra storage on our phones. Actually, I don't. Moreover, as I've said many times, the only way to be prepared to learn when you come to class is if you've looked at your notes and or videos from the previous class. Generally, that means spending 10 or 15 minutes the night before or the morning before you come to class and looking through your notes and seeing what you understand and what you don't understand, and making sure that you ask what you don't understand at the beginning of class. So why don't we start that with saying, are there any questions?
If we don't have information about like the device or the valve in the transfer function schematic you have up here,
Yeah.
like how do you use that information? Like how would you?
Are you talking about it here?
Yeah.
When you say device, I know what you're talking about valve, but what device are you talking about?
I guess it like an analyzer or something?
Yeah, well, generally, if you want to do a problem, you need information about everything. You need information about the valve, you need information about the measurement device. When I give you a problem, if I don't give you that information, then you assume that it's just one. You assume that it's given as one. In real life, that is not in the course, you don't make those assumptions, you go out and measure them. Now, we spent some time in the last class actually deriving GV for a valve, and where Y is the position of the plunger in the valve that closes the valve. And its GV is V prime tilde, the volumetric flow rate through the valve. It's change from the initial value and plus transform divided by Y prime tilde, where Y prime tilde is the change in the position of the stem of the valve from its initial position taken to a plus transform. And you can see that because in GV, the input is the signal from the controller, and the output is Y. So actually, I think I have that wrong. The output is the typically a volumetric flow rate. Typically, the output is a volumetric flow rate, and the input, actually, let's just make sure I got that right before I go on. Yeah, the manipulated variable adjusts the position of the valve stem, and the output is typically something like a volumetric flow rate. Of course, I don't want to put those in here because that depends on the example. The input to the process that's being changed by the valve doesn't have to be volumetric flow rate, but it often is. So basically, what we found was that this GV was just equal to a constant. KV, and we determined what that constant was using the energy equation from unit ops, where A was the cross-sectional area of the valve, F is the fanning friction factor, L is the length of the valve, delta P is the pressure drop across the valve, rho is the density of the fluid, and 2 is a number, and Y0 is the initial position of the valve. So this whole thing is what we call, is what we see as KV, and we can see that KV depends on the square root of delta P. So if I change the delta P, I change KV. But KV for fixed delta P is just constant. Questions? Okay, so let's see where we were at the end of the last class. What we were doing at the last class was we were looking at, of course, the feedback loop. Here we have the feedback loop where we can have a disturbance or a change in the set point causing changes in the system. Here we have the control variable, and we found that the control variable is measured to give by some measurement device that could have a transfer function, usually CVM. That's compared with the set point, and if they're not the same, there's an error. That error is non-zero. That non-zero error is fed into the controller. The controller has some sort of algorithm, and the input is the error, the output is a manipulated variable, which often is an electrical signal, or it could be something telling the valve what position to go into. A GV is the final element, which is often a valve, but it doesn't have to be a valve. It's the one that the controller sends a signal to change some sort of input into the process. Often that's a valve. We like valves because we can control them from a distance, and they're fast, and they're generally reliable. Then we have the process transfer function, and the result of the disturbance going through its transfer function and the control system going through its transfer function add, and they give us a control variable. So that's the feedback loop. And by looking at this block diagram, we're able to determine CV prime tilde, that is, to determine the control variable, the Laplace transform of the change in the control variable from its initial position, in terms of SP prime tilde, the change in the Laplace transform of the change in the set point from its initial value, and the D prime tilde, the Laplace transform of the disturbance. And we see that we have two effective transfer functions for SP prime tilde and D prime tilde in terms of the transfer functions, the individual transfer functions, GD, GP, GV, GC, and GS. And we had two examples that we were referring to over the course of the last week or two. That is, whenever we were looking at different control systems, we would test them out on a linear system and a nonlinear system. There's nothing special about these examples. The reason they were chosen is because the linear system, this one, and I should actually put a separate box around this because this GV is separate. The linear system, which was basically where we monitor the temperature, the output, theta, and we have a flow coming in with a certain temperature, and we monitor the temperature at the outlet, and if we don't like it, we measure that temperature, we can just adjust the flow rate of a cooling stream coming in. And what we did last time, and here we noted that the heat transfer coefficient for this heat exchanger depends on the volumetric flow rate of the cooling flow in a way that we looked at earlier in the semester as ABC to the B, where A and B are constants. And we went through the details of calculating exactly GP and GD, what KD and KP were. And we did that in detail in the last class. But the main thing is that both of them are first order. This is a first order system, 1 over 1 plus S. For this case, with 3 CSTRs in series, again, the control variable, maybe I should be specific here, is CA3. Here the control variable is theta. The manipulated variable here, the thing I change, is the volumetric flow rate of VA. Here the manipulated variable, is VC. And the disturbance variable here, was XAB. That is the concentration of A or the mole fraction of A in the normal feed. Whereas here, the disturbance variable was theta in. And what was interesting about this case, the only thing that made this interesting, was because they have three CSTRs in series, the GP and GD were both cubics, so they were not first order system, but they were third order. That's the only thing, the only reason we chose these two examples. We wanted to have a first order system and a third order system, because the first order system has unusual properties. First order is unusually stable. It's the exception, not the rule. The rule are nonlinear systems, so here is a typical nonlinear system. And what we did in the last class and a half is we started, well actually the last couple of classes, when we introduced this, is before we got to control, before we did introduce this, we were only observers. There was no control. If we were observers, we were only looking at this portion here. D prime, GD prime, CV. With no control, all we had are systems that had a disturbance, the transfer function of that disturbance, and that gave us a control variable, and there was no reaction to that. We were just observers, and we learned how to do this, how to determine GD, and how to determine what's going to happen to the system. Is it going to be stable? Is it going to be unstable? How does it react to oscillatory inputs, etc. At the beginning of what we were doing with control, we said, well, with feedback, we're going to introduce this entire loop. And you can notice that without this, we call it open loop because there are no loops. It's just a straight line. Once we have feedback, we look at what's coming out and we react to it. If we don't like it, if it's not equal to our set point, we have a whole system of trying to nudge it back to the set point. And that's why this is called closed loop for obvious reasons, because it just is a loop. Clearly, if I had no control, that's like putting GC equal to 0. If GC is equal to 0, then this is 0 and this is 0, so the set point doesn't matter. If I don't have control, the set point is doing nothing because I just have disturbance and system. And if I don't have control, GC is 0, so I just have GD times D prime tilde, which is exactly what we were doing the rest of the semester, in the early part of the semester. So then we were talking about, okay, great, we have this feedback control loop. This is feedback. Now let's look to see what are options for GC. Well, there are obviously an infinite number of options, but the most useful and the most standard one that was developed in the 1940s, so 80 years ago, and it's still the most frequently used, is what's called the PID controller. And what we did is we looked at each of those individually. P is proportional, I is integral, D is differential. And we noted, and maybe I should even have another column with what MD is for these. Maybe I'll just put it underneath. Here I have MV prime tilde is KC. Why don't we do it this way? GC, which is MV prime tilde divided by E prime tilde, is just equal to KC for proportional. And for proportional, that is, the amount MV is changed is just proportional to the error. And what we find is that the nice thing about this is fast. If I have a big error, there's a big response. But the offset doesn't go to 0, that's bad, and it doesn't anticipate. If the error is small, but it starts to go up quickly, until it goes up, the proportional control doesn't really respond. So these are good and bad. This is supposed to be a plus, not a 1. Pluses and minuses. For the integral, we had GC was equal to KC, the integral E of T prime, dt prime, from 0 to T, divided by theta I. And this, the integral control, the good thing is it kills off the offset. The bad thing is that it's slow, you have to wait a while until the integral of the error actually builds up, and it doesn't anticipate. It's the opposite of anticipating. You have to wait not only for the error to get big, but for it to be big for a long time. So it's very slow. On the other hand, it has no offset, so it complements the proportional control. Finally, there's differential control, which anticipates. Even if the error is small, and it's been small for a while, if it starts to go up, and it has a quick derivative, it looks like it's going to get big, you don't have to wait for it to get big. The differential control says, things are starting to go wrong, let me react before they get too big. So the differential control really anticipates. The problem with differential control is if you only relied on differential control, you'll get really big offsets, even worse than proportional control, often as bad as if I had no control at all. And also, if I have noise, high frequency noise, which is very typical, then differential control will constantly be turning the valve on and off all the time, and that will break the valve. So typically what you have is that for each negative offset, there's no offset. For no anticipation, there's anticipation. For slow, there's fast. So what you find is that for each negative, there's another mode of control that has a positive. And so that's why we often use a combination of proportional, integral, and differential, because if I balance them nicely, then I can take care of all three. I can have it reacting not too slowly, no offset, and have some anticipation. You can imagine if I have the balance of these three wrong, if too much differential, then things get screwed up. It's going to be terrible because the valve's going to be going on and off. If I have too much proportional, then, and I didn't actually write this here, GC is KC times DE dt times TI. I think I called these tau I, and this was tau D and tau I. Theta. So I think this was tau I. So as I was saying, if I have too much proportional control, then what we saw is you can get instability, very easily go from a system that's stable to one that's unstable. So I don't want too much of this, I don't want too much of this. If I have purely integral control and not enough proportional, it's going to take forever to actually get to the set point. So the PID controller, if you tune it correctly, by tuning I mean choosing the three parameters, KC, tau I, and tau D. If you choose them well, you can get excellent performance. Maybe not optimal for a particular system, but pretty damn good. And this is extremely versatile. It works on many, many different systems. But if you choose the parameters poorly, you can get terrible results. So you can get anywhere from terrible to great. And what we're going to spend some time on, probably beginning the end of this lecture and the next lecture after the exam, is we'll talk about actually how to find these parameters, how to find good values for these parameters. But what we were doing was we were doing a demonstration. Whenever we introduce something new theoretically, then we would like to test it out on our examples. And one example, the example we were doing last time, was this particular example, the first order example. And we looked at a situation where D prime was 0, so there's no disturbance, but there is a change in the set point. And I'm going to repeat a little bit of what I did at the end of the hour. Here is theta prime tilde over SP prime. The control variable is theta, so it's CV prime tilde over SP prime tilde. So that's CV prime over SP prime tilde, D prime tilde is 0 by assumption. And I'm going to assume that we have proportional integral control. No anticipation, but proportional integral. It's too warm here. Again, if there's anything you don't understand, just stop me. So let's notice that what we have here. We know KP, we know we know GP, We know GC. And what do I need? I need to know GP, GC, GV. We know GV is just KV. So, and I'm going to assume that GS is equal to 1. So let's notice GP, GV, GC. GP, KP over 1 plus ST. GV, KV. GC, KC 1 over 1 plus STI, tau I. And now the denominator, 1 plus the same thing times GS. GS is 1, so the denominator should just have the same thing. KV, it's exactly the same thing. So there we have that, and now what I'd like to do is just put it in a little nicer form by multiplying top and bottom to get rid of these denominators in the denominator. And I can notice that 1 plus S tau I, if I just put that under one denominator, that's 1 plus S tau I over S tau I. So I'm going to multiply top and bottom by 1 plus ST times S tau I. So if I do that, I have theta prime tilde over SP prime tilde. So I'm multiplying top and bottom again by 1 plus ST, tau I. So if I do that, I have so I'm multiplying top and bottom by 1 plus ST, S tau I. And just to make life a little easier, I'm going to divide top and bottom by KP, KC, KV. So when I multiply, I get rid of this, I get rid of this, and I get rid of this. So I just have 1 plus S tau I in the numerator. And in the denominator, okay, so I multiply by 1 plus ST, I multiply by 1 plus by S tau I, and divide by this. So what I'm left with in this particular term is just 1 plus S tau I. Which is no surprise because this term is the same as the thing in the numerator. But what I'm left with in this term is everything else, because this was 1. So this is 1 plus ST, S tau I, divided by KP, KC, KV. If I haven't made any mistakes. So the 1 is multiplied by all this cancels out, and the other things are exactly what they should be. So the first thing is let's look at the find the value theorem for theta prime tilde, where SP prime tilde is a step function, so I have delta SP over S. And let's see what we get. So this says that the limit as t goes to infinity of theta prime tilde is equal to something. It's equal to the limit as S goes to 0 of S, this is theta prime of t, theta prime tilde of S. And let's see what that is. Now, let's anticipate. Before we actually look at the solution, let's anticipate. Since I have proportional integral control, I expect it to be relatively fast and there to be no offset. What does it mean, no offset? If I have a disturbance, no offset means I go back to where I started. If I have a change in the set point, no offset doesn't mean I go back to where I started. I started at the old set point. No offset means I go to the new set point. Is that clear? No offset means I go to the new set point and not somewhere else. So let's see what that is. So this, so I have the limit as S goes to 0 of 1 plus S tau I, 1 plus ST, S tau I, KP, KC, KV, 1 plus S tau I. So that's just this thing. Now I have to multiply by S, and I have to multiply by SP prime tilde, which is delta SP. over S. Okay, so the S is canceled. And let's notice what happens when I take the limit as S goes to 0. As S goes to 0, this goes to 0. This whole term goes to 0 because there's an S in the numerator. And this goes to 0. But I'm left with a 1 up here, and I'm left with a 1 down here. So this just gives me delta SP, which is exactly what means no offset. I'm going from my long-time behavior is to go to the new set point. I started at the old set point, I go to the new set point. So as expected, this is no offset. Well, so that's great. Let's look at, since this is a first order system, and we said first order systems are sort of unicorns, they're outliers. One reason they're outliers is not only that they're super stable, but generally we could also do all the algebra in gory detail, which we usually can't do with the nonlinear system. So we can actually invert this. So why don't we go through and just rewrite the denominator. So I have theta prime tilde over SP prime tilde is 1 plus S tau I divided by, and let's just write it out. So I want to write it out as a quadratic equation. So here I have S squared times T tau I over Kp, Kc, Kv. That's the quadratic term. And then I have S, so there I have times tau I times 1, that's this term. And here I have S times, let's see, the S term, that's going to be this one. So it's S tau I times 1 over Kp, Kc, Kv. So that's the 1 here. I've taken care of the S squared, so the only thing left is 1. So if I haven't made any mistakes, which there's no guarantee, but I have a quadratic in the denominator, as I expect. And notice, why do I have a quadratic? Just as in the last class, even though this is a first order system for GP, by having the integral, integral control, notice this integral control gave me a 1 plus S tau I. It gave me, so the fact that I have this integral control means I had to multiply through by another S tau I, which means the integral control was like another first order system in series. So I had the process and the integral control as two first order processes that combine to give me a second order system. So even though the process itself is first order, the integral control is like another first order system. So the two of them together give me a second order system. And you can see that because I have a quadratic in the numerator, in the denominator. All right, well, let's look at this quadratic equation. Remember when we looked at general second order systems, for general second order, we wrote the denominator as 1 plus theta 2 squared S squared plus 2 theta 2 CS plus 1. Let me write it this way. S squared theta 2 squared plus S times 2 C theta 2. So this thing would be 2 C theta 2, and this thing is theta 2 squared. If I want to put it in that generic form. So let's notice what these things are. So here's Blackboard 2. So theta 2 is then the square root of T tau I over Kp, Kv, Kc. And all those quantities are positive quantities. So that's, well, easy to see. And C is just equal to tau I times 1 plus 1 over Kp, Kv, Kc. That's this thing, divided by 2 theta 2. Where theta 2 is right here. So I can calculate C and theta 2. And the important thing is, this quantity is, theta 2 is strictly greater than 0, because everything in it is greater than 0, and I'm not subtracting anything. And here I have a bunch of positive quantities. So this is also greater than 0. So I have nothing suspicious. And if you remember, the stability is always determined by the roots of the denominator. And when this is the denominator, then I know that the roots, say S1 and S2, or I call it S plus or minus, the roots, are again minus B, so it's minus 2 C theta 2, plus or minus the square root of B squared, 4C squared theta 2 squared, minus 4AC, 1 times theta 2 squared, over 2A. 2A is 2 theta 2, theta 2 squared. And if I cancel a 2 in the numerator and denominator, 2 goes here and kills off the 4's, because they're in the square root, and I can cancel a theta 2. Theta 2 kills the theta 2 squared in here. I'm left with minus C plus or minus the square root of C squared minus 1 over theta 2. So what can we see immediately from here? What we can see immediately is, first of all, if C is greater than 1, if C is bigger than 1, so two cases. Case A, C greater than 1. If C happens to be greater than 1, and it's not clear from here, it depends on the parameters, whether it's greater than 1 or not, it's certainly greater than 0, then the discriminant is positive, so I have a real solution, and the magnitude of the square root of the discriminant is less than C, because I'm subtracting something from C squared, so that says that even when I add, I get something negative. So if C is 1, both roots are real and negative. So it's overdamped. Meaning it just goes exponentially to the result. No oscillation. Stable, no oscillation. Case B, however, where C is less than 1, and obviously greater than 0. In that case, the discriminant is negative, so the roots are complex. But with negative real part. The real part is C over theta 2. Negative C over theta 2. But with negative real part. So underdamped, that is stable, but with oscillation. In other words, here, wherever it's going, it goes there without oscillation. And here, wherever it's going, it goes there with oscillation. They're both stable, but one oscillates, the other one doesn't. Any questions on that? Well, we can do actually a little better. Now we can actually try to invert this. Let's try to invert this. And let's notice how do we invert it. Well, notice the denominator has a quadratic. Well, actually, let's look at it. So I've got theta prime tilde is equal to, as we said, well, I had it over here, but let's write it out. I have 1 plus s tau I divided by s squared times t tau I. Actually, let's just leave it as theta 2 squared. Theta 2 squared plus s times 2c theta 2 plus 1. And if I multiply that by s prime tilde, which is delta sp over s, then I can notice that the denominator is a quadratic times s, and the numerator is 1 plus a quadratic, 1 plus sp. And that's something that we can invert exactly. In fact, you can notice that, actually, why don't you tell me to make sure that you're actually awake? What line in the table has a quadratic times s in the denominator? you said? That's a very specific quadratic. That's not the quadratic we have, a more general quadratic. What other line has it? That's, of course, where both roots are the same. Line 8. 17. If I look at 17, I have exactly this denominator, but what do I have in the numerator for line 17? 1. So that's good for this term. What about for this term? Is there another one that I might be able to use here? 15. So let's look at 15. 15 has a quadratic in the denominator, but no s in the numerator, no s in the denominator. But that's okay, because when I look at just this term, the s's will cancel. So with lines 15 and 17, I can invert it. So let's first do the 1. So if I do the 1, that's line 17. That says, let's take the delta SP out. So from the 1, I get 1 minus, 1 minus 1 over the square root of 1 minus c squared, e to the minus c t over, and let's see what tau is. Tau is theta 2. Right? Yeah. Times the sine of the square root of 1 minus c squared over theta 2 plus 5. So this is the part from line 17, and the part from line 15.
Professor, and what happened with the t, the little t?
Here it is. Did I lose a t here? Yeah. There should be a t here. Should also be in here. Thank you. And then from line 17, I'm sorry, from line 15. In line 15, for a equals to 0. So line 15 with a equal to 0, then I have to multiply by tau I. That gets multiplied by c over tau, c over theta 2, times e to the minus tc over theta 2, times the sine of the square root of 1 minus c squared over theta 2 plus phi. And I have two different phi's here, so let's call this phi 1 and phi 2. And let's calculate, let's see what c and theta 1 and theta 2 are. I'm sorry, c and phi 1 and phi 2 are.
Professor,
Yep.
once again, the little t.
Did I lose a t?
It's tiny, right?
Thank you. I don't know why I keep leaving that out. Okay, thank you. So let's see what c is. Remember, in line 15, a is 0. So if you look at c, the first two terms in the numerator involve a, so they're both 0. So c is just 1 over the square root of 1 minus c squared. How about phi 1? Phi 1 comes from line 17. That's the arctangent of the square root of 1 minus c squared over c. And phi 2 is equal to, from line 15, the arctangent of 0. And the arctangent of 0 is just 0. So this we can just get rid of. C we can just write as 1 over the square root, 1 minus c squared. And phi 1 we'll just leave alone. It's the arctangent of this thing. Okay, so what can we see from this? First of all, let's just verify that, first of all, it's kind of nice that we can actually invert it. And we get the full time dependence. And what you can see here is that the time dependence, it oscillates. It oscillates with the sine function whenever C is less than 1. If C is less than 1, then this is 1 minus a quantity that's less than 1. So the square root of that becomes a positive number, and I have a frequency here, it oscillates. Well, that's exactly what we said. When C was less than 1, both roots are complex, so we get an oscillation. However, what happens if C is greater than 1? If C is greater than 1, then the discriminant is negative, and the square root of that is imaginary. So what do I mean by the sign of an imaginary number? Recall that the sign of, say, AT is equal to e to the IAT minus e to the minus IAT over 2I. So if A happens to be imaginary, so if A is equal to IB, for example, then this becomes e to the minus BT minus e to the plus BT over 2I. Over 2I, yeah. And let's just make sure that e to the minus, yes, correct. So if I multiply top and bottom by I get minus I times e to the minus BT minus e to the plus BT. So notice there's no sign anymore, nothing oscillates. It's just I have a linear combination of, an exponential plus and exponential minus. So the only time things are going to oscillate is when C is less than 1. When C is greater than 1, I don't have the oscillation anymore. And if you're worried about this I, remember that the sign is multiplied by the square root of 1 minus C squared, so I'll have another I here that will cancel it. So the I's will go away, and this will be perfectly real. Same thing here, the sign and the square root here. So the I's will go away, and I'll just get something perfectly real. Let's also notice what happens at long times. We said from the final value theorem that I just get delta SP. Well, as t goes to infinity, the exponential kills this term, and the exponential kills this term. The only thing left is 1, and that's multiplied by delta SP. So that actually agrees as well. The other thing you can notice is another way, since we've already factored it, since we know what S plus minus is, you can also write the solution from line 10. If you look at line 10, another way of writing the solution is line 10. We could write theta prime tilde is equal to, from line 10, which is exactly of this form, 1 plus something divided by a factored quadratic times 1 over s. So here I would just get delta SP times, and now A is just tau I. So here I have, this is multiplied by 1 plus, let's see what tau 1 is. Tau 1 is 1 over the root. Okay, so let's notice I need to know what tau 1 and tau 2 are. Tau 1 is minus 1 over tau 1 is equal to S plus, and minus 1 over tau 2 is S minus. Or here I have S plus and S minus. So S plus tau 1 is just equal to minus 1 over S plus, and tau 2 is equal to minus 1 over S minus. So that would just give me minus 1 over S plus minus A. We said A, in this case, is just tau I, divided by tau 2 minus tau 1, minus 1 over S minus plus 1 over S plus, minus tau 2, which is minus 1 over S minus tau I, divided by tau 2 minus tau 1, 1 over S minus plus 1 over S plus. So this is a convenient form as well. It's a little easier to write, It's a little bit less explicit, and this is of course, but then you have the S plus and the S minus can be complex numbers. So this is maybe a bit more useful.
Okay, so we don't have exponential? We don't have exponential? For the minimum?
Did I lose the exponential? Yes, I lost the exponential. Thank you. So this is multiplied by e to the minus t over t2, which is s2 plus s minus t. And this is e to the es plus. Thank you. Don't seem to be doing a good job copying. Better when I know things by heart than when I forgot them. So I have these exponentials, and that solution is completely equivalent to this solution. Well, this one we're able to see a bit more. Okay, so what do we say here? I've kind of shown all of the things that I wanted to show. First of all, immediately from here, we can see it can be over-damped or under-damped, but it's always stable in either case. And the nice thing is that there's no offset. We're able to see that directly or from the final value theorem. Are there any questions on that? Okay, so now if you remember, we said it's great. Typically we don't want the control variable to be oscillating too much, and we do want it to have no offset. But we also don't want the GV. We also don't want the valve to be going on and off, because that would break the valve. So we should look at the input to the valve, the manipulated variable. So what is let's turn our attention to the manipulated variable. If we turn our attention to the manipulated variable, mv prime tilde, it's related to cv prime tilde. Let's say I'm in a situation where d prime is 0. If d prime is 0, then I know that cv prime tilde is equal to, from the block diagram, gp gv mv prime tilde. So remember d is 0, so gp gv times mv prime tilde gives me cv prime tilde. So right from here I can see that mv prime tilde is equal to gc sp prime tilde divided by 1 plus gp gv gc gs. I see it immediately from here. Because I know that when I multiply by gp gv, I'm going to get cv prime tilde. So what does that tell me? Notice the denominator here, this denominator, is the same as the denominator for cv prime tilde. So that tells me if there's an instability and cv is going crazy, mv is also going crazy. And it's going crazy in the same way, because it has the same roots. Meaning, if cv as a function of t, and mv as a function of t, if cv starts growing, mv will also start growing. It may grow in the opposite direction to try to balance it, but if this thing is going up and down, then mv prime is also going up and down, and it's going at the same frequency, and it's growing in the same amount. The same, if it's exponential growth, it's growing at the same amount because it's controlled by the same denominator, which has the same roots. And the roots of the denominator are controlling whether something is over-damped or under-damped, whether something is stable or unstable. If it grows exponentially or shrinks exponentially, if it shrinks with or without oscillations. The same result, it's the same denominator for for cv prime tilde and for mv prime tilde. They're governed by the same stability characteristics. Also, even if things are good, even if cv prime tilde shrinks, mv is still going to be going on and off too much, just because to counter this. So even though I may be happy that cv is going to its anointed value, and to its set point, it may not be a good thing if it's underdamped and it's oscillating, because that's going to make sure that MV also oscillates. And if MV oscillates too much, it can break. Now, and you know, as I mentioned, the nice thing about this particular example was we can invert it, and that's because it was the first order system. Nonlinear systems we generally cannot invert, and that's why it's great for things like the final value theory. Now, you might say, control. Do I ever see control in real life? You know, control, it's in this course. I may see it when I go to work. Do I ever see it in real life? Well, you know, if you live in an old apartment building, then your toilet may have a tank. Does anyone have a tank in their toilet? Or you've all seen tanks in the toilets? That is a control system. It has a control system. When you flush the toilet, you open the valve on the bottom and the water comes out. And then you have a float switch. And when the float switch is down, you have a little tube at the end. And when it's all the way at the bottom because there's no water in the tank, then that controls the valve. The valve is the liquid coming into the tank. And as it goes up, the valve starts to close. So the liquid in the tank is my control variable. The liquid level in the tank is my control variable. Initially, the liquid level is 0 because there's no water in the tank. I have a control system. That says I'm going to control the valve. And I'm going to make sure that valve is open. I'm going to make sure that valve is open when it's all the way at the bottom. And the higher it goes, the smaller the error. The smaller the error. So therefore it starts to close the valve. And when it gets to the top, it shuts the valve completely. So this, in fact, is a control system. Now, of course, you have to determine GP. It's not too hard to determine GP. It's a good exercise to try to do. You can see this control system in action. And then you might ask yourself, well, what happens if, as happens often, the gasket wears out? That is, you have a valve at the bottom that closes the tank, and it has a gasket. So when the valve closes, it's sealed. Sometimes when the gasket wears out and you have to replace it, water still goes out. It never seals completely. What happens in that case? That's an interesting question. But this is an illustration of what we've been doing here. It's a simple illustration that you come across every day. And you come across lots of control systems every day that you may not realize. Now, also, I want to emphasize to you that and I've said it before, that questions of stability with control are completely different from questions of stability without control. With control and without control are different. Why are they different? Because without control, so let's look at the situation without control. With no control, GC is 0. This term is gone. There's no influence of the set point. And the denominator is just 1. So without control, the stability is governed. Without control, CV prime tilde is just GD times D prime tilde. So stability comes from denominator of GD. With control, stability is from denominator 1 plus GP, GV, GC, GX. So what does that mean? Notice that in the denominator of GD, let's say in this example, in the denominator of GD I have 1 plus ST cubed. Well, here, even if I had a 1 over 1 plus ST cubed, I would also have a plus 1 here. It's a different denominator. It's a different polynomial denominator. It has different roots. So by adding control, if I'm really clumsy, I could take a stable system and make it unstable. Or if I'm clever, I can take an unstable system and make it stable. So there's a whole range of things I can do there. Are there any questions on that? Okay, so any questions on this? So this completes the material on what control is, or on the PID controller. And now the question is, how do I tune a controller? How do I find KC, tau I, tau D for a given system? And what I mean here is good values. How do I do that? And that's called controller tuning. That's called tuning. So that's obviously a very important question. If I decide, as we mentioned, a PID controller could either be great or horrible, or anything in between, depending on whether how good I am at choosing those parameters. The good thing is, one advantage of the PID controller is there are only 3 parameters, KC, tau I, and tau D. There are only 3 parameters. And if you were at last lecture and or watched the video, you notice that there's a KC in all 3. I didn't have to use the KC here. I did it for units so that the new parameter would have units of time. So here, the parameter units of time takes care of the extra t in the denominator of the derivative. Here, the parameter that is units of time takes care of the extra t in the integral. So that's why I kept KC around. But really, the parameter in GC is independent of this parameter, because whatever I want it to be, I just adjust tau I to make up for whatever KC was, and similarly for tau D. So that's why I keep KC in all 3 of them, just so my new parameters, the other 2, have time units. But there's no particular dependence there. So there are various ways of tuning my parameters, of finding these parameters, and we're going to talk about a few of them. In order to do that, I need a process model. That is, I need a GP or a GD. I need a model, and I also need a controller element. So am I using PID? Am I using PI? Am I using PD? Am I using ID? Etc. I need to know which controller I'm doing. Because if I use a PID controller, I get different values for my parameters than if I just use a PI. I need to know which one I'm doing. And basically, before I even start this process, we need to realize that every model is an approximation. All models have errors. Even fashion models. They fix it up on screen, on the computer. Everyone has errors. No model is perfect. On the other hand, when we install a control system, we design our control system based on an imperfect model, but it has to work on the real thing. So we have to be cognizant of that the parameters we find, theoretically, we may have to retune them on the real system. So what does this tell me? This says tuning is a 2-step process. Kind of like the West Coast Liberty, 2-step. Step 1 is general tuning. And by general tuning, that's where I choose the parameter values based on the model. And then there's fine tuning. I don't necessarily, so the general tuning should get me good parameters based on the model, but then I have to tweak them a little bit on the real system because I know that my model is not perfect. So, and we'll talk about how to do both of those. So let's first start with general tuning. With general tuning, again, what we want to do is what are our goals? We want to get 0 offset. Let's look at some goals. 0 offset, stable system with control. And we want to minimize oscillations of MV. So those are our goals. We don't want the system to be unstable. When it's stable, we don't want it to oscillate too much. And connected with that, we want to minimize the oscillations. We want the system to be stable, and we want it to have the MV not to oscillate too much. And as we saw here, MV oscillating is the same thing as CV oscillating. So we don't want CV oscillating too much, because that's going to mean MV is going to oscillate too much. And how do we determine, we usually need a measurement of the error. And the typical error measurement we talked about a bunch of them, is the integral absolute error, IAE. In other words, where the IAE is the integral of the absolute value of E of t prime dt prime from 0 to t. So we're not usually interested in the point error. We're looking at the integral error, and we want to minimize that. We usually want to minimize this. And we use the absolute values so when we're above the set point and below the set point, they don't cancel out. It's bad to be above, it's bad to be below. We don't want them to fix each other. So we use the magnitude. And we take the integral because things can be bad for a little bit of time, but we want them to be good over long periods of time. So that's why we're talking about the integral. And that's typically what we want to minimize. So how do you do these? Well, there are various ways, and we're going to look at a few ways. So method 1 is called brute force. Sounds very tough. It's actually the dumbest method, because brute force usually is pretty dumb. And the second method we're going to talk about is correlation. So what is brute force? Brute force means usually you have a choice. You can think or you can be brute force. So brute force has the least amount of thinking. It's saying, me have big computer, me solve equations. So the basic idea there is I try to solve equations as much as I can and see if I can come up with a solution. Now I want you to note that, did I lose a page here? Oh, here it is, yeah. I want you to note that all these methods are numerical. There isn't an analytic method for coming up with the controller tuning. They're numerical. So if I'm going to come up with a method here, I need sort of a way. Every system is going to be different. Every system is different. So I would like, remember I said I need a process model. So what I'm going to do here is I'm going to take a process model that is flexible enough, it's a reasonable approximation to many, many systems. So let's choose a process model. Is very versatile. Well, let's think back. Let's see how to choose them. If you remember, we said first order systems have this basic feature. They sort of go exponentially to where they're going. And they're very stable. if you remember, when we have first order systems in series, then I take the discontinuity from the input, so let's say CSTR. If I have a discontinuity in the input, if I have one CSTR, the discontinuity is in the input. If I have two CSTRs in series, and the output, so if I have a discontinuity in the input, the output is continuous in time, but the discontinuity is in the derivative of the output. Whereas the input, there's a discontinuity in the input, in the output there's a discontinuity in the derivative of the output. If I have two CSTRs in series, then the output of the second CSTR, there's a discontinuity in the second derivative. The first derivative is continuous. If I have n CSTRs in series, there's a discontinuity in the nth derivative, but not in the n-minus first derivative. Moreover, what we saw was that the more CSTRs I have in series, keeping the total tau the same, the more the system starts to look more and more like a plug flow reactor. So I hope you remember that. The more CSTRs that I have in series, as long as I keep the total tau the same, the more the overall system looks like a plug flow. The more each CSTR starts to look like a cross-section in a plug flow reactor. So remember, in a cross-section, there's mixing in a plug flow reactor. Each cross-section is uniform, but there's no mixing in the z direction. In a CSTR, there's complete mixing in one CSTR, but there's no mixing to the CSTR behind it. It just passes everything on to the CSTR in front of it. So you can see how many CSTRs in series, as they get smaller and smaller, start to look more like cross-sections of a plug flow reactor. A plug flow reactor is, we thought of it just as a delay if there's no reaction going on there. Because if you have a plug flow reactor, if you have a change going at the inlet, since it's a plug flow reactor, nothing happens for tau seconds until you see that exact change at the outlet. So if I take a first order system, in series with a delay, I get a system that has features. If the delay is 0, then I have the features of a first order system. If the first order features are not important, then I have something that looks like a plug flow reactor, essentially an infinite number of first order systems in series. And by balancing the two, by having different coefficients in front of each, I get something that is a rough model of many, many systems. So that's why we choose this. As for any real system, we try to fit the coefficient of, we write this as a first order system times a delay. So that is, we write G tilde of this system as 1/1 plus ST. Then I have a KP, and I have delay e to the minus ST. So by tuning KP and theta and T, KP, theta, and T, so I tune KP, theta, and T to fit an arbitrary system, to fit my system, as best as possible to this model. So once I have a KP, and I know what control system I have, so now I have a system model, and once I know what control system I have the equations, I can start solving them. In fact, you can use Simulink to solve them. You should practice Simulink. You can use Simulink to solve them. So how do I now use that? So I'm going to assume that this is done already, that I have a KP, I have a theta, and I have a T. Theta is the delay, KP is the steady state gain, and T is the time constant for the first order system, which, as you remember, when you write a first order system, you've got ddt of the dependent variable plus something divided by a constant. And that constant is the time constant, that's T, is equal to the stuff that the forcing functions, all the effects of the forcing function. due to the disturbance or due to the manipulated variable. So recall, in general, a general system, you've got d dependent variable dt plus some stuff divided by a time constant is equal to a g for the gd times d prime tilde, is disturbance, plus a g for the manipulated variable times mv prime tilde. So this was sort of the general form that we had, where we had a disturbance. So for example, in this system, on the right side of the equation, we had an xav prime tilde, which was the disturbance times something, times the gd. And we also had a something times va prime tilde, which was the manipulated variable, which gave me the gp. There. Okay, so how does it work once how does it work? How do I do the this particular the brute force? Well, what I do is I pick some constants, pick values of tau I, tau d, kc. Just pick those values. And I solve. And I solve for CV of t, CV prime of t. And I might get something. And then I calculate integral absolute error. And then what I do is I leave tau I and tau d alone and try different for fixed tau I, tau d, vary kc. And if I do that, then I can plot integral absolute error versus kc. And this is at fixed tau I and tau d. And hopefully I'll find the minimum. So this is the minimum, the best kc for that value of tau I and tau d. So this value is kc star, which depends on tau I and tau d. Then what I do is I do this, then I start varying tau I and tau d. So this is brute force, it's a lot of calculations. That's why it's brute force. And then what I can do is I can look at, let's forget tau d. Let's vary, now I vary tau I. And if I plot the kc star versus tau I can plot, these are curves of constant integral average error. And when I get some sense of these curves, so this might be a bad integral absolute error, this is a little better, this is a little better, this should hone me in on a best integral absolute error. Now, notice I said, let's ignore tau d. Why do I want to ignore tau d? First of all, I can do the same thing with tau d now, but tau d is generally going to be quite small. The reason tau d is going to be quite small, so there isn't much of a range of tau d. And the reason for that is because there's always noise. There's always going to be noise. If there's always going to be noise, I never want the coefficient for tau d to be too big. I never want the coefficient for d to be too big. If the differential part is too big in the controller, then the slightest bit of noise is going to drive the controller crazy. So I have very little wiggle room for tau d. I might make it 0, but if I want some anticipation, I'm going to have a small value compared with tau I and Kc. So I don't have a lot of wiggle room, and that's why I didn't worry about that here. And this is called the brute force technique. Are there any questions on that? Okay, so in the remaining minute or two, as we said, there are typically errors in my model. Every model has errors. And it's typical that model errors are equivalent to about plus or minus 25% on each parameter. Plus or minus 25% each parameter. When I say each parameter, I could mean these parameters, Kp, theta, and T, but also 25% on each of these three. So what I would do as a final step is I would do 6. I would do 27 simulations. I would take each of the three parameters, Kc, tau I, and tau D. And I would take its value minus 25%, and the value plus 25%. So I have 3 choices for Kc, 3 for Ti, 3 for Td. I would do 3 times 3 times 3 simulations and pick the best one. Pick best IA. So as you can see, this is called brute force for a good reason. There's very little physical thought here. This is basically just me have a big computer, me do lots of calculations. So the caveman approach. Caveman with a computer. Okay, so I'm gonna stop right here. And we'll continue with the correlation method next time. But where next time means after Thanksgiving, when you've had lots of tofurkey, or real turkey. Next class, we have an exam. And the exam will cover everything up to, not including feedback. Everything before feedback. So I think it's chapters through chapter 5 or chapter 6. I don't have the book in front of me.
4, 5, 7, and 8.
No, 7 is feedback.
7 is feedback. And 6 we didn't do. So I think it's just through chapter 5. So remember, what does that include? That includes Laplace transforms. Everything you always want to know about Laplace transform, but we're afraid to ask. People seem to be afraid to ask things in class. Stability, response to oscillations, etc. These are all what's in there. I gave you homeworks. Fewer and fewer people were doing the homeworks. Let me remind you that doing homework is the way you learn the material. You come to class, you're watching the movie. But if you watch a movie about how to fly an airplane, you don't know how to fly an airplane until you get in there and you fly the airplane. The homeworks are flying the airplane. So you really have to do the homeworks. And again, the time to figure it out, it's a little late now for this second exam, but not for the final. The time to figure things out is not 2 days or the night before the final. It's after every class, it's to figure out what you don't